Hi, this is Hilal. In this video, we will look at the properties of Nash equilibrium and we will see whether it is actually unique. So first property, we will see whether it is unique. Okay. Second property, we will see whether it always exists. Always exists. And third property, we will see whether it is Pareto optimum. Pareto optimum or Pareto efficient. Okay, we will see whether these properties are in the Nash equilibrium or not. Okay, now let us focus on the first property, whether it is unique or not. For that, we will form a payoff matrix of a game. Okay, we have player A, and he has two choices to make, either to go top or to go bottom. Okay, bottom. And similarly, we have player B on this side. Player B has also two options, either to go left or right. Okay, let us have the payoffs for this very game. Let us say we have, for player A, if he goes top, he gets 2 as payoff. If he goes bottom, he gets 0 as payoff. Similarly, if player B goes left, he gets 1 as payoff, and if player B chooses again left, when player A chooses bottom, he gets 0 as payoff. Similarly, we have 0 0 here, and we have 1 2. Okay, now let us see whether in this game we have a unique Nash equilibrium or not. By unique Nash equilibrium, we mean that there is only one Nash equilibrium possible. And how do we find the Nash equilibrium? We find the Nash equilibrium when both the values in a cell are encircled. Okay, and by Nash equilibrium, and I have told you in earlier video, Nash equilibrium describes the optimal state of the game where both players make optimal moves. But now consider the move of their opponent. Okay, now let us see whether this game has a unique Nash equilibrium or not. Let us say player A chooses stop. Okay, player B has two options, either to go left or right. If he goes left, he gets 1 as payoff. If he gets right, he gets 0 as payoff. Okay, so he is better off going left, so we encircle this very value. And remember, the first numbers in these cells represent the payoff of player A, and second numbers uh, represent the payoff of player B. Okay, now this was the case when player A chooses top. Let us see what happens if player A chooses bottom. If player B chooses bottom, again the player B has two options, either to go left or right. Okay, so when player A chooses bottom, player B has two options, either to go left or right. And here we can see going right gives him 2 as payoff. Okay, and going left gives him only 0 as payoff, so he will choose 2. Okay, now consider what happens when player B chooses left. If player B chooses left, player A has again two options, either to go top or bottom, and going top gives him 2 as payoff, going bottom gives him 0 payoff, so 2 is greater than 0. That means player A will choose to go top. Okay, now let us see what happens if player B chooses right. Again, player A has two options, either to go top or bottom. Top gives him 0 as payoff, bottom gives him 1 is payoff. Obviously 1 is greater than 0, so he will choose 1 here. Okay, and here we can see we have two Nash equilibriums. Okay, I am not using drawing them in cells uh, because to make it more simpler, and it will get messy if I try to form cells. So I will now try to form them in cell. Okay, it is not actually uh, necessary, but for the sake of simplicity I am just making them into the 4 cells. And here we can see that player B, sorry, in this game we have two Nash equilibriums. So uh, whether the Nash equilibrium is unique, by unique we mean the payoff matrix or the game has only one Nash equilibrium, but here we got two Nash equilibriums. That means Nash equilibrium is not unique. So we say Nash equilibrium is unique. No, Nash equilibrium is not unique. Okay, because we got here two Nash equilibriums. So we can say that Nash equilibrium is not unique. Okay, now let's see whether it always exists or not. For that, we will use the same players, player A and player B, and we will change the payoffs here. Okay, let us say if player A chooses top, player B chooses bottom, we have the payoffs of 0 0. Okay, we have 0 minus 1, we have 1 0 and minus 1 and 3. And remember the first values in each cell shows the payoff of player A, and second numbers shows the payoffs for player B. Okay, and we will check whether it always exists or not. So let's try to see whether this game has Nash equilibrium or not. By Nash equilibrium we mean when both the numbers in a cell are encircled. Okay, that means when the players choose their optimum moves among the strategies. So let us see if player A chooses top, player B has two options, either to go left or right. Going left gives him 0 as payoff, going right gives him -1. So he will choose 0 because 0 is greater than -1. Okay, let us see what happens if player A chooses bottom. If player A chooses bottom, again player B has two options, either to go left or right. And here we can see going right gives him 3 as payoff and going left gives him 0 as payoff. So the player B will choose right. Okay, so encircle this number. Now let us see what happens if player B chooses left. If player B chooses left, player A has two options, either to go top or bottom, and bottom gives him 1 as payoff, which is greater than 0, which he gets if he chooses top. So he will choose here 1. Okay, similarly let us see what happens if player B chooses right. If player B chooses right, player A has again two options, either to go top or to go bottom. And here we can see top gives him 0 as payoff and bottom gives him -1. Since 0 is greater than -1, so he will choose 0. Okay, and we can clearly see not both the values in a cell are encircled. So we can safely say that this game has no Nash equilibrium. That means Nash equilibrium does not exist for this very game. And we can say that Nash equilibrium does not always exist for a game. Okay, so whether Nash equilibrium always exists? No, it does not exist always. And I have told you, if both the values in a circle, sorry, if both the values in a cell were encircled, then we would have said that it exists. And here we can see only one of the value is encircled in a cell, and we can say that Nash equilibrium does not exist for this very game. Okay, so this was property second, and let us see the property third, whether it is Pareto optimum or not. And we have to see here. For that, we need to take the prisoner's dilemma game. That is, we have two players or prisoners. We will write players here. Okay, so we have player A, player A. Okay, player A has two choices. Actually, prisoners. It is prisoners. I will write here players. So we have two prisoners. They are being confined in two different cells in a prison, and both uh, the prisoners have two choices, either to confess. So let me write here, confess or deny, either to confess the allegations or deny the allegations that are being imposed on them. Similarly, we have prisoner second or player second. Let us say we have player B. He has also two choices, either to confess or to deny. Okay, now let's draw the payoff for this very game. Let us say if player A confesses and player B also confesses, then player A gets -3, that is 3 years of imprisonment, and player B also gets -3, that is 3 years of imprisonment. Okay. Similarly, when player A denies and player B confesses, player A gets 6 years of jail or imprisonment, and player B gets 0 years of jail. So he is freed there. Okay. Similarly, what happens if player B denies or player A confesses but player B denies? In this case, player A gets 0 years of imprisonment, but player B gets 6 years of imprisonment. Similarly, what happens if player A denies and player B also denies? In this case, let us say both get 1 years of imprisonment. Okay, this is the famous prisoner's dilemma problem. Okay, let us see whether this game has first Nash equilibrium or not, and then we will see whether it is optimum or not. Okay, let's try to see. Let us say when player A confesses, if player A confesses, player B has two options, either to confess or deny. If he confesses, he gets 3 years of jail. If he denies, he gets 6 years of jail. So he will choose to confess here. Okay, let us say when player A denies, player B has again two choices, either to confess or to deny. Confessing gives him 0 years of jail, denying gives him 1 years of jail. So he will choose 0 here. Okay, now let us see what happens if player B confesses. Okay, let us say when player B confesses, player A has again two choices, either to confess or deny. By confessing, he gets only 3 years of jail. By denying, he gets 6 years of jail. So he will choose, let us say, this, because -3 is greater than -6, so he will choose confess. Similarly, what happens if player B denies? Player A has again two choices, either to confess or not. Okay, and here we can easily see that the player A will be better off if he chooses to deny. Okay, and in this game we can easily see both the numbers in the first cell are encircled. Okay, and we can say that this game has Nash equilibrium. Okay, we got the Nash equilibrium for this very game, but whether this whether this Nash equilibrium is Pareto optimum or not. Let's try to see. Okay, so first we got the Nash equilibrium. Now what is meant by Pareto efficient? Pareto efficient means making better of someone without making others worse off. Okay, that is the definition of the Pareto optimum. That is a, uh, a move, or what we can say, we say a policy is a Pareto optimum if it makes one better off without making others worse off. Okay, here we can see if there was some sort of arrangement, that is if prisoners agreed. Okay, if there was an agreement before entering into the cell that both prisoners agree that whatever happens they will deny. Okay, if they would have made their mind that they will deny whatever happens, then deny, that is if both deny both persons deny, then we could have said that uh, this very option, when both player A and player B denies, then we could have said that this deny was a Pareto improvement. Okay, so it would have happened only if prisoners agree that whatever happens they will deny. In that case, we could have said that this very strategy was Pareto superior. Okay, otherwise our Nash equilibrium was -3, that both players will get 3 years of imprisonment, but they could have made themselves better off if both of them have chosen to deny. If there was some sort of agreement between these two prisoners before entering the cell that they will deny whatever happens, then we could have said this very strategy, that is deny, deny, could have been, or I can write here is Pareto, Pareto superior, or Pareto improvement. And here we can see this uh, Nash equilibrium which we got here, this -3 and -3, is not Pareto optimum. Both the players would have been better off if they would have chosen to deny at all. Okay, so we can safely say that this Nash equilibrium is not Pareto optimum. There can be a Nash equilibrium, okay, but there can be another choices for the players in for both the players. In that case they would have been both better off. Okay, so in this case we can easily say that Pareto optimum is not always a Nash equilibrium. Okay, sorry, Nash equilibrium is not always the Pareto optimum. So I repeat what is meant by Pareto optimum here. So by using the Nash equilibrium, the prisoners will get 3 years of imprisonment each. But if there was some sort of arrangement between the prisoners that they will deny whatever happens, in that case we could have said that this -1 would have been a Pareto superior. Okay, strategy for both of the players. Okay, so we can say that Nash equilibrium, though we got the Nash equilibrium, but it is not Pareto optimum. This deny, that is getting 1 years of imprisonment, would have been Pareto superior, or what we call the Pareto improvement. Okay, so we can say here confess is Pareto inefficient. That is confess, confess, that is the strategy when both confess is Pareto inefficient. Why it is a Pareto inefficient? Because there was other as there was other permutation and combination. Here we can see there were other choices. They could have been both better off if they would have chosen deny and deny, and we say this is Pareto superior. Okay, and this confesses Pareto inefficient. Okay, I hope I make myself clear in this video. If you like these sorry if you like these videos, please share and subscribe with your economics friends. That is only motivation for me to keep going on. Okay, and let me reiterate that I'm just a student of economics. In that capacity there can be some errors in my videos. I'm I am trying to make the videos error free, but it happens, it is human error here, that I could have committed some mistakes in making videos. So please rectify me if there are some mistakes in my videos. Thank you. Have a nice day.